Good afternoon, everyone, and welcome to today's ENS webinar, Nuclear Energy and Data Center Meeting the Energy Needs of Digital Expansion. I'm Lancelot Diallo from Tractable, and I will be the moderator for this webinar. So we are witnessing a rapid development of artificial intelligence and cloud computing, which are accelerating the expansion of data center around the world. This data center requires a significant amount of electricity. And at the same time, we are seeing an increasing number of announcements linking the digital and nuclear sector. Major technology companies, data center operators, and energy providers are exploring new partnership and long-term agreement to secure reliable, scalable, and low-carbon electricity supply for the decade ahead. These growing conventions highlight how closely the future of digital infrastructure and energy system may become connected. As a result, important questions are emerging from policy makers, utilities, technology companies, and society as a whole. How will the growth of data center reshape the electricity demand? What are the implications for power system planning and grid reliability? Can nuclear energy provide the scale, stability, and low carbon generation needed to support this digital expansion? Today's webinar, we explore this question through international perspectives with EPRI, one of the world leading independent energy research organization, and insights from the French experience with EDF. We will start with EPRI for 20 minutes, then we let the floor to EDF for again 20 minutes, and after that we will have 20 minutes for Q&A, and you can put your question on the chat. So let's start with EPRI with Daniel Klein. So Daniel, you are the lead for advanced reactor engineering at EPRI, where you oversees the nuclear beyond electricity, commissioning, operation readiness, probabilistic risk assessments, civil engineering, and the maintenance focus area within this advanced nuclear technology program. And before joining EPRI, you spent 18 years at Framatome, where you held various roles, including project manager, project engineer, and supervisor in system and components engineering organization. Daniel, the floor is yours.
Okay, thank you very much for the introduction. So I will start my screen share. So can you see the full slide deck, or do you see the presentation mode?
The presentation mode.
Okay, perfect. So that should be good. So yeah, good afternoon, everybody. Thanks for having me. So for those of you that don't know EPRI, so we are a global research organization. So we have over 700 utility members and over 300 companies worldwide. EPRI exists for over 50 years. And to give you a feel for the annual research budget that we have, so it's about $500 million every year. So at EPRI, like I said, we're a global organization, and here, since this is a European webcast, we want to showcase our European footprint. So our European headquarters is in Dublin, Ireland, but as you see on the map here, we have representation in many countries in Europe.
Daniel,
yeah.
Sorry, we are stuck with the first slide. We can see the whole deck. So we don't see the slide that we want to show, the first one.
Okay, let me try that one more time. I apologize for that. So,
Okay, good.
all right.
No, it's better.
Okay, I think there was a delay. So do you see now the European location and key research area slide?
Yes.
Okay, perfect. All right. Yeah, so that was what I was talking about. So our European headquarters is in Dublin, Ireland, and as you see here on the map, we have a footprint in various European countries. Our research includes highlighting our, besides the data center work, in energy storage, cybersecurity, hydrogen integration, and of course, in my area, we do a lot of nuclear industrial integration, which includes data centers, but also petrochemical application, pulp and paper, desalination, mining, etc. So I advanced the slide on my screen. Just want to make sure that this caught up on the video share. So do you see now our values and guiding principles slide?
Yes.
Okay, perfect. All right. So I think we're good to roll. Okay, so real quick on EPRI, as I said, we are a research institute, and so our values really the integrity, being objective, having a public benefit, and we really drive from collaboration with our members and our innovation that we lead and then create the value for the members, but also for society. So now when we look at how we want to power basically and support the power industry, of course, there's a hardware component, a software component, validation, and really the AI topic kicked off the last 2 years. So we started to work on nuclear integration with data centers about 3 years ago already. But like I said, it really took off over the last 2 years. And AI is a big topic at EPRI. So we have various initiatives like DC Flex, this flexible operation of data centers, as one to highlight. But we also have like various AI integration initiatives like the Open Power AI Consortium and the work that I do in nuclear integration with data centers. So I think everybody here on the call has seen various growth projection from the AI and data center demand. And just as a quick going back in time, basically, so there was a first wave in the early 2000s, but as you see, turn on my laser pointer. So as you can see, there wasn't much of a growth. Then there was a second wave where the cloud really came up in the 2010 to 2020. Again, was fairly flat, but now really with that AI boom, this is where the uncertainty really kicks in. And as you look at various growth projection, it's a very wide span from a low to a medium to a high, where you see it's anywhere from to 800 terawatt hours from 200 terawatt hours. So that's a factor of 4, just uncertainty of how much that really materialize. And the other slide that I want to show is there is a comparison between how much there is a growth projected in the United States and in China and in Europe, just to stack that up, that people understand, okay, what do we see across the regions? Now, leaving that introduction and the highlight here, we dive now into really the work that we are doing on EPRI on data centers. So in my area, of course, nuclear power traditionally was used to provide electricity to the grid. Now we also look at, okay, electricity can be behind the meter or in a microgrid provided to a data center. We also looked at using nuclear heat for cooling with absorption chillers, for example. And then the topic comes up, yeah, we can also use fuel cells initially to power data centers while we're waiting, nuclear gets built out, similar to we run a natural gas turbine or plant initially. So with that nuclear cosmos, as you know, we can make electrolytic hydrogen, for example, that can be provided to fuel cells or backup power. But this is just a side area. So the real focus currently we have is leveraging heat that comes off from a data center, recognizing its low-grade heat, like 40 degrees Celsius or less. But then when I boost it with nuclear power that I have available, especially when I look at advanced reactors, we have on the Rankine cycle over 550 degrees Celsius available and boost that. It opens up a wide range of industrial processes that I can provide heat to. Of course, if I just connect a data center process heat with greenhouse, I need low temperature in the 40 degrees, so I don't need that full nuclear implementation. But when I look at petrochemical integration, most of the processes are 300 degrees Celsius or higher. I need a higher temperature heat that I can use. Same thing on desalination. If I look at MED or MSF, like multi-stage flash or multi-effect distillation. So I have to be over 100 to 150 degrees Celsius. So we can tailor that depending what our heat end use cases. Here are a couple reports, and for those of you that are not familiar with EPRI, if you just Google EPRI and punch in these numbers, you have access to the reports. Some of them are free to the public, like the first one here, for example. This is really a high-level guide for those that start about thinking integration nuclear with data centers. Then we have a dedicated report about behind-the-meter electric loads and really what does it take to connect behind-the-meter load with a nuclear power plant, even for a retrofit project, or if you start with a greenfield application. Also for the reactor designers, as they standardize the design and basically in the standardized design have already a tab, so to speak, for behind-the-meter connection integrated. So that is a guidance document for that. A minute ago, I talked about the thermal energy storage system for nuclear integrated data centers. So this is a report that we are wrapping up in the third quarter this year. We are also writing currently with hyperscaler and engineering companies that build and design data centers a new guide that goes in great detail of how we integrate nuclear energy with data centers. Way more in-depth compared to that introduction guide here. So that will also be available in the third quarter. And then what I'm going to talk about the rest of the presentation here, that's really that impact assessment, data center driven load burst on either a co-located or a physically closed data center as a nuclear power plant. So what are the challenges when we talk about AI training and fluctuating loads, right? So I assume most of us have seen some kind of power fluctuation graphs. When you have a data center that typically provides like cloud service, the fluctuation of energy demand is fairly flat. Typically, it's between 10 to 15% over the time of the day, and a lot is caused by when people come to the office and also the outside temperature that really drives the cooling need. And what you see here, that green mosaic, if you will, that is the GPU cluster and the racks and when they perform walks. So you see more of a harmonic distribution, and that reflects in that flat power curve. Now, when I look on the right side where I have an AI type data center, these GPUs are clustered together. That means if they get a query to execute a task, so they kick in a cluster factor, and that's why we see these power spikes. And the problematic factor is they have within sub-seconds these fluctuation, and depending on the size of the data center, we are talking megawatts of electricity demand that kick in and then basically drop back to an idle stage. And this is what we call these fluctuations. Now, of course, these shapes can be different depending on what you exactly have in that data center. Each data center, or a lot of data centers, are different. They can have some AI component, they can have some cloud component, or they can be mainly cloud or mainly AI. So the problem with these flickers is that they cause some oscillation. And as we look at the co-location of a nuclear power plant, and that's what you see here on the right side. So I have my nuclear power plant, provide electricity to the grid. But if I have a data center that is basically behind the meter connected, or even if that would be on a grid, but very physically close or next to a nuclear power plant, that fluctuation that the data center causes and the electricity demand has an impact on our steam turbine shaft connection. So what you see here is basically it's a high pressure turbine, intermediate pressure turbine, low pressure turbine representative model. So the steam drives the turbine on the nuclear power plant. And then that is connected to a shaft, and that drives an electric generator that provides electricity either to the switcher, then to the grid, or in a direct connection to a data center. Now, with these fluctuating electric loads, they can excite a torsional mode. And what that is basically, it's a frequency range of that rotating shaft. And the definition here is on the bottom, because I recognize not everybody might be familiar with that. So a torsional mode is that specific natural angular vibration pattern that occurs around axis of a rotating shaft. So in other words, these fluctuating loads can hit the same frequencies that we have these torsional modes of the various components in. And that can lead to short-term or long-term fatigue. I mean, short-term fatigue can be to a point that it hits the natural frequency of the shaft and that more or less it destroys it immediately. But it can be also like that you have a constant, more subtle fluctuation that can cause long-term fatigue. And at EPRI, we have seen fatigue problems with that turbine generator shaft in the past from electric fluctuating loads, what you see sometimes in the steel industry, where they have some electric ovens that induction heated. They can have these fluctuating loads. We have seen that on military applications. They have a radar system. They can have some fluctuating loads, and they can really be hot on the shaft. And other components. So what you see here on the slides is not only the nuclear or not only the shaft components, but all the other ones. So in order to speed up and recognize the time limit that we have here, so basically every turbine shaft or every turbine and generator connection is different depending on the size of the components. And therefore, they have various frequencies that are critical and we want to stay away from. Now, what EPRI is doing, we have tools to model the interaction between a data center and your rotating equipment. In our case, it's a shaft on the nuclear power plant. But the same is also true for any rotating equipment from a gas plant. So it's not a nuclear unique problem, but since we are I'm from the nuclear sector, I look at this from the nuclear lens. So we do the modeling where we have basically grid system, and then we plug in data centers. Basically, here in this case, that is a behind meter connection to a large nuclear power plant. But we also have configurations where we have a data center that's connected to the grid, but co-located to a generation asset, and basically use the waveforms, that is the fluctuation and the power quality. Basically the load profile that comes out of the data center feed that in our tool and see how that excites the turbine generator shaft. So here's an example where we used a frequency where we had a data center that's 120 megawatt data center. We let that fluctuate at a 6 hertz example. We know this is a non-torsional mode. That means it's not a critical flicker pattern. And look at the results here. So we basically see there's not much of an impact on these various rotating masses. So you see that line remains fairly flat. Now, if we go into a frequency that we know it's sensitive, we basically here we calculated the same, or we had the data center creating a fluctuation of 15.83 hertz, and then you see a massive spike in the oscillation load and the effect on these rotating masses, and that is exactly our research that we are working on, and we are working with data center companies and engineering companies that build data centers. And as they implement their UPSs, battery energy storage system, eStatComs, and so on, they can simulate for future data centers what frequencies they put out on the grid, depending on how they operate the data centers. And we use that information as our input to see what it does to the generating asset in our case, the nuclear side. Yeah, so I think I'm getting close on my time limit. What I want to highlight here, EPRI runs workshops. So, for example, on the US side, we have in mid-August, and it's a 2-day event where we just look at nuclear integration with data centers. So that will be in North Carolina. So for those of you on the call that would like to join that event, it's an in-person event, so I have to say that we don't offer a virtual option for that, just to have better engagement. As you receive the slide after the events here, there's a registration link that you can register. And later this year, we also have a European workshop where EPRI, the nuclear team, comes to Europe. That will be in Budapest in October timeframe. So if you're interested in the European workshop, please let me know. And just to give you a flavor, and that's my last slide here, for what we typically cover in these workshops. So I just want to highlight a couple of things. So we will talk about thermal energy storage system integration. Of course, there will be a way longer session on that data center fluctuating load and the impact on the nuclear power plant, but we also talk about community integration, nuclear insurance considerations, of course, carbon-free electricity, nuclear microgrids, industrial microgrids, water consumption, power purchase agreements, life cycle assessment, supply chain challenges, how we measure the waveforms in order to have reliable data that we use as input to our tools, and some additional integration concepts. They will be in front of the meter, but beneficial to the utilities. And with that, I think I reached my time, and I'll wrap up. And I think we are either have questions later, or Lancelot, how do you want to go about that?
Yes, we will have the question later on. So thank you, Daniel. Thank you for this very interesting presentation. So you briefly start by describing the electricity demand from hyperscaler around the world, and then you explain the possibility of microgrids and multiple combination of electricity and heat for nuclear and data center. Finally, you describe the main challenges of direct connection of data center with nuclear or behind the meter, with the fluctuation load, and more specifically with the AI training. This fluctuation load can increase the fatigue and ultimately leading to turbine generator shaft failure. So now let's switch to get some insight from EDF with with Caroline Bonneau. So Caroline, you have a PhD in mechanical engineering and scientific computing from the Michigan University. And after a postdoc and some job as a researcher at Lawrence Berkeley National Laboratory, you joined EDF in 2008. And now you are a senior research engineer and you lead a research project on hyperscaler. Caroline, the floor is yours. We cannot hear you.
Oh, sorry. Thank you very much for the invitation. Yeah, my mic was not good. I'm just going to share the presentation. You should see it in large.
Yeah, perfect.
Is that good? All right. So today I'm going to speak about the context of data centers in France and the different initiatives that we have. All right, so I'm going to start with giving you a global overview of what France is in the worldwide data centers. So in 2024, the energy consumption of data centers was about 420 terawatt hours. Europe represented about 16%, and France represented 10 terawatt hours. So that's about 2.5% of the global worldwide energy use of data centers. If we look for 2024, so the USA, EPRI already, I think it has jumped. Are you still seeing the presentation?
Yeah, the second slide.
All right, okay. Yeah, because on my slide, actually, I saw that it had disappeared. Okay, on my Teams. All right, so in the USA, it's about 44% of the global energy consumption of data centers, and China represents about 25%. And then if we want to go a little bit further forward in time, and so this EPRI also showed some of those curves, and I'll just put it back so that people can remember. So if we look at the IEA, they actually made projection about a year ago. And so we see that there's a very large rise of power consumption for 2030, 2035. And I took the base scenario, which is a turquoise one. And so here the projections are 946 terawatt hours. Out of those terawatt hours, Europe would use about 12%, and the projection for France are 15 to 20 terawatt hours, which represents 1.5 to 2% of the worldwide energy used by data centers. If we look at the rest of the world, for example, the USA is 45%, so about what was in 2024, and China is about 29%. So if we go now deeper into France, so France has two world-scale data center hubs, which come from the geography. So the pictures are a little bit old because they're 2022, but the numbers have changed, but the distribution remains the same, which is why I kept those pictures. So what you see is that maybe I should have my pointer. All right, so you have the Paris area, which is around here. So you see that this is where you have most of the data centers. And you also have data centers spread throughout France. And when you see the power of data centers, so most of the data center power is around Paris. And you see another area over here, which is around Marseille. And it's around Marseille because when you look at the subsea cables, what you see is that you have a lot of cables that are arriving from Asia and the Middle East and Africa through Marseille. And this is a data center hub over here. So if we look now at the growth of data center expected for the next decade, so here we find the numbers I talked to you about in the previous slide. So at 2030, which is the range that's given by RTE, which is the French TSO that does some of the previsions. And what we see is that in 2035, there's a larger uncertainty on the range. And if we compare to their previous prospective exercise, which is in a dotted line here, we see that potentially there could be a higher level of data centers. So now we're going to look at how we can, what are the different advantages of locating a data center in France. So over here, you have the map of France with Paris here, Marseille over there. And you have, this is a 400 kilovolt network, so the high voltage network in France. So it's fairly well meshed. And then, so to locate it, you need to have available power. In France, the power is also low carbon. We also have available grid connection. The prices are competitive. So we are able to also find land, like powered land, to install those data centers. And there is a support at the state level. So regarding the available power here, what you have is that you have the net export of power for France from 2005 to 2025, which is the last year. This one is still in progress. And what you see is that, so if you like, on blue you have the exports, in purple you have the imports, and in turquoise this is the net between import and export. And so what you see is that since 2005, on average, France has been exporting about 50 terawatt hours, and the last two years, in 2024 and 2025, the net export reached 90 terawatt hours. And so 90 terawatt hours, just to give an idea of what it is, it's the consumption of a country like Belgium. And in France, the global consumption is 450 terawatt hours about, so it's about 20% of what the country consumes. So then, now that if we look at the type of electricity that's being produced, if you look on the graph on the bottom, what you see is the share. So it's so you have the production and the share of a decarbonized production. And here you have, so in yellow you have nuclear, then you have hydro, wind, and then solar. And so what you see is that most of the share of the production of electricity in France is highly decarbonized. And as a consequence, if you look at the intensity, the carbon intensity in grams of CO2 by kilowatt hour, you have, which are on this axis, the numbers are fairly low. And for the last 2 years, for example, the numbers are around 20 grams of CO2 per kilowatt hour. And if we compare with countries, for example, around France, the numbers are more like around 200 or 300 grams of CO2 per kilowatt hour as a comparison. And so then once you have the power and decarbonized power, you need to be able to connect to the grid. So if you have a hyperscale data center, so it's a data center that's over 100 megawatt, you need to be connected to the transport network. And so for the data centers that are between 100 megawatts to 400 megawatts, you could connect to the 225 kilovolts. And then after 400, you need to be connected to the 400 kilovolts. So the network that you saw on the map a couple of slides ago. And so today, if we look at how many data centers are connected to the transmission grid, what we see is that, so we have this graph that comes from the TSO, from RTE. And what we see that in 2025, we have about 1 terawatt hour of power consumption from data center that is connected to the transportation network. And RTE in one of the public conference had mentioned a couple of months ago that there were 8 data centers that were connected to the transportation network. And so so that's now if we look at what's available. So last year, RTE communicated on the current grid availability in France. They said that there was 50 substations that had a connection capacity of 250 megawatts, and 20 substations that had a capacity of 750 megawatts. So that's for first numbers. Then there was a process that was validated last year. That's called fast track. The fast track process is for larger projects, so between 400 megawatts and up to a gigawatt. It's a connection to the high voltage, so the 400 kilovolts network. And the guarantee is to have power by 2028, 2029. And they have identified 8 sites in France. 5 of them have been published. And so this is a possibility that's been offered for example, data centers. And then there is globally RT, so the TSO, the TSO is having a plan for developing the network. And so the way they go about it is that they have defined several zones. They are the P1 zones and the P2 zones. So the P1 zones are the one that you see in pink. They correspond to a lot of the French ports, and where you have a lot of consumption, and they have been identified for reinforcements. And here you have, for those mutualized zones, the timeline that they expect to have the reinforcements. And so those reinforcements can serve different usages, whether industrial usages or digital usages. So data centers were taken into account. And then you have other zones, so the P2 zones, which are the ones in turquoise, that have also been identified as zones for network development. All right, and so that's like how they physically anticipate for the grid connection, and also they have published this particular graph where you see like how much reserved power they have for different projects. And so the reserve power is about 30 gigawatts, which is higher than most of the industry connected in France today. And so what they see is that you have the projects that have really being realized and that were put in service since 2023. You have the ones that are constructed, and then you have the ones where they have signed they signed a contract or reservation with RTE, which are over here, which represents almost like maybe 12 gigawatts, something like that, with data centers, hydrogen, and industry. And then you have for the timeline 2025 and 2029, and they have the ones for 2030. And those ones are the ones that are on hold and the ones that have been abandoned since 2023. And so the way the process worked is that the first one who had put in the demand to be connected was the first one to be served. And so there is a shifting that's being done with public. So there's a process to validate the shifting with different different public consultations, and to move away. So from this first arrived, first served to a first ready, first served. And so here they just have a graph to explain how this could work. So here you have the timeline with the different time from 2025 to 2030. Here you have the network capacity. that you could put on the network. And here you have different projects. So the first project, which is in green, was the first one to request the connection, and it's going this way. And here, here you have this project that needs this much connection. Then you have the 2, the 3, and the 4. And so if you get the traditional first arrived, first served, then you can develop the project only in 2030, so that you can connect to first customer and then second, third, and fourth. Whereas if you go to the first ready, first served, then you could, for example, connect the second and the third first, and then connect the first and the fourth afterwards. So that allows to have a better use of the network. All right, so now as far as prices are concerned, so here I have a map of the CAL 27 baseload for Europe. And what we see on this map is that France is fairly well positioned as far as prices are concerned for the in Europe. Also, there is a possibility to subscribe a CAPN, which is a contract for allocation of nuclear production, which gives an access to a share of generation from the nuclear fleet. This is meant for large consumers, and the volume is 1,800 megawatts for delivery starting on January 1st, 2027. So this is one of the possibilities in France for large consumers. And there's a strong support at the state level for data centers installation. For example, there was in February 2025, there was the AI Action Summit. And so here there were 35 sites that are installation ready that were disclosed. And so the sites are, so here you have the dates at which the lens would be available and the surface that you could have. And so you see that they are among different regions of France, some of them around the Paris area, and some of them also around the Marseille area, and some of them in other regions. In May 2025, there's also Choose France, where there were a lot of announcements of investments for infrastructures and AI services with, for example, Amazon, Brookfield, or Digital Realty. In February 2026, there was a 1 year or so, there was a map that was released to give a summary of the different projects and where the different projects were at after the AI Action Summit, where the map and the sites were released. And very recently, in May 2026, there was Choose France again, where there were investment announcements for infrastructures and AI services, which are the ones that actually put on the slide. There were others, but I focused on the digital ones, and where you have as well new investments that were announced at that occasion. And so so this is giving a map from February 2026 with different projects and the different. So you have the name of where the project lies. You have the name of, for example, the company that is developing, and you have also the status, whether they are, for example, like some of them in the northern part of France are, the request for interest is still ongoing. So people can still show that they are interested. And for some others, there are started construction. Some others are actually finalized construction or in the connection process. So this is this gives you an overview of the different contexts and the different possibilities in France.
Okay, thank you, Caroline. Thank you for this very interesting presentation. So after briefly describing the situation of data center in France, including their geographic distribution and power capacity, you have described all the advantage France has to offer as a location for data center. Now let's start with the Q&A. So as a reminder, you can ask all your questions on the chat. And maybe I will start, Daniel, with one of mine. And in your presentation, we can see that AI training can cause a lot of load fluctuation that could negatively impact the turbine and the shaft in nuclear facility. If I understand well, it was more in the case of behind the meter or direct connection. What are the solutions that are currently available to reduce or even eliminate this risk?
Yeah. So it basically requires a collaboration between the data center company and EPRI or another organization that can basically look at the waveform that comes out of the data center and how that affects really the grid or the co-located rotating machine. So there are ways by using battery energy systems, e-STATCOMs, UPS systems to shave and limit some of the oscillation, but they don't have a good design target, like in terms of what is an acceptable reduction or what frequencies do you have to stay away from. And this is really why we work with companies like hyperscalers, engineering companies that build and design data centers. So as we bring new data centers on the grid, to avoid basically being proactively to do an assessment where they connect and what is that connection, basically what is the impact to the grid or to the rotating equipment or spinning machine that is close by. You know, like I said, in our case, it's a nuclear generator, but it can be also a fossil plant. It's the same problem. And yeah, so there's hardware available that can mitigate it, but you need a design target to understand here are the frequencies you want to stay away from. And in order to determine the frequencies, you need to understand your rotating machine and what torsional modes you want to stay away from. So it's basically a communication effort between the data center company and the grid or the engineering company analyzing the grid.
Okay, thank you, Daniel. Here I have a question in the chat from Philip. So during a recent seminar in London organized by Core Power, the use of floating nuclear power plants to supply electricity to data center was highlighted. Can you comment on this, on the advantage, if any, of building floating nuclear power plants and near-coast data centers? Daniel or Caroline, if you have any comment on this.
I can take a first step maybe, since we look at maritime application on nuclear as well. So of course there's way more unknowns at this point in terms of regulatory requirements. If I have a floating nuclear power plant right now, I mean it's already a challenging timeline to get nuclear power plant built on land. You know, if you put that on a barge, you know, and ship it to an harbor and connect it, there's way more regulatory uncertainty. Like I said. Technically, it's feasible. There are power generation assets on a ship that get floated in a harbor and connected. So I'm not sure if there's a real advantage at this point. Maybe down the road, if that becomes a mainstream thing and these ships or barges are deployable, you may save some time. when it comes to actual deployments. But as it stands right now, the data centers are really looking at speed to power. How fast can I power my data center? And what is the best way? So I'm not sure if they really answered your question, if there's a true advantage at this point. I would say if you go down that path where we stand currently, it might be a longer time to power your data center. But in the future, if you really have a factory assembled floating nuclear power plants that can pull up in an harbor, or you connect a power cable, it's oversimplifying that. But there might be a speed to market advantage, but there are also other options with microreactors that you can deploy at a shorter time frame and so on. So I think we have to see how that all shapes up and pans out in the future.
Okay, thank you. The second one, do you have a view of how much gigawatts of AI training will be likely done in Europe versus the US? I think it's a tricky question, but it's good to have an overview of specific AI training.
I'm hesitating giving a solid answer because you saw the spread. There's a factor of 4 uncertainty. So the AI training, the way I see it, it might be a limited thing over the next 5 years, until the AI training, or maybe 10 years, until these training models are further dialed in and are really established. And maybe at this point, you transition from an AI training load more to an AI search, if you will. So in terms of gigawatts, I don't know if that is, and really depends on the time frame that you're looking at. Right now the projections till 2030 are probably more reliable. And that can be, depending how fast you build data centers. It can be anywhere 5 to 15 gigawatts, but you have to bring the power online. Really, that is a challenge. And right now we see a huge uptick in natural gas power plants that are getting deployed because the nuclear timeline cannot support it. Of course, there are power upgrades and restarts of nuclear power plants to support that race, basically. But yeah, that's where that is.
Okay.
Yeah. Also, what you see is, as far as the load of AI versus other types of usage of data centers, is that it's actually shifting with time. Depending, first you have a certain percentage of your load that's going to be AI training, and then it's going to evolve because once you've trained once you have used your data to train your models, then you're going to be going into a different type of zone.
Yeah, true. Here we have another question. Can nuclear really compete with gas power plant or combined cycle to cover the fast-growing power needs in data center? We know that in the US they are using a lot of gas power plants to fix their issue of load. Is it clear it is clear that we can use the available existing capacity to have a piece of the cake, but new nuclear could arrive too late. Does nuclear have any ace up their sleeve or not evident advantage? I know that nuclear have already one good advantage of low carbon electricity. I think this is one of the main advantage, but maybe you have other idea.
Yeah, so in terms of the speed to power, right? So what we see in the United States, the natural gas peak exists, but they also have challenges in terms of lead times to getting key components, right? Natural gas turbines, there's only so many suppliers that build them, and they are basically sold out for years now. So also you have to have the natural gas pipeline and the pressure in the pipeline to support the amount of electricity or natural gas to convert into electricity available. So they run into some bottlenecks as well, and the interconnection agreements and so on that has to be approved. So 3-5 years timelines are now getting becoming the norm. And when you look at this point, we have first of a kind deployment of small modular reactors, like in Canada, they're building the GE boiling water design, the BWRX 300. So as we come down that learning curve, and you can deploy SMRs down the road in 5 to 8 years, we are kind of getting closer to natural gas. And like what Lancelot was saying, a lot of the hyperscalers, they have aggressive zero carbon or carbon-free targets in their corporate policies or in their corporate commitments, right? So they start off as natural gas because that's what they need now. But in the long term, as we look like many years down the road, nuclear will probably be a valid source. And it might not be a single source that every single data center that gets deployed will have a nuclear power, but there are other sources, that will stay on the grid. But I think the trend will more go towards carbon-free electricity. And as we know, nuclear is a reliable option, So I think the data center boom will continue. I don't believe that we really will kind of flatten the curve at one point, because each time you send an email, each time you take a picture with your phone, that all goes to the cloud. There is information that gets exchanged constantly. More people have more intelligent stuff in the house. Every printer has a wireless connection. I mean, there's so much data that needs to be processed. So I think the demand for data handling will go up and continue to grow, and therefore the data centers will grow.
Okay, thank you. Do you consider or have evidence that co-locating data center and nuclear power plants may cause mutual induction of regulatory and or licensing issue or restriction?
Do you want me to take that role? But I don't want to answer all the questions. So maybe Caroline, if you want to cover that. If not, I'm happy to speak to that.
Just you can do it, yeah.
Okay, so yeah, it depends on the market environment, I would say. If there's a problem from the grid operator or regulatory point of view, right? So we have, for example, in the United States, we have a regulated and deregulated market. So in a deregulated market, like in Texas, for example, behind the meter is accepted from the grid operator. So there won't be as much of a regulatory problem, so to speak. Of course, there will be always, as you co-locate nuclear power plant with data center, and you have an electric integration and then heat integration potentially down the road for cooling, there will be some licensing consideration. You have to look at transients like large load rejection in terms of electric loads or heat loads, if you have a cooling integration. So there, it's certainly doable. The regulator will be involved, but the grid operator will also be more in favor compared to the way you have it in another area where the grid operator really owns and controls everything. They don't want to have a behind the meter or microgrid in their area or territory of responsibility. So it's really a regional topic, I would say. And in some areas and some region it works. In some region, it might not be acceptable, or you get a lot of headwind, and pushback.
And I can complete with France. So the way the way that when we had like large loads, so industrial loads, the way it was done is that, for example, on the large industrial areas, is that you would have a large producer, such as a nuclear plant, that would be feeding to the grid through a substation. And then the large industrial consumers would actually get their electricity through the grid. So, for example, if you look at in Dunkirk, where you have the largest single point, which is making aluminium, this is the scheme that is used. So it goes through the network, and as far as cost is concerned, there is as a large consumer, there is a reduction of cost for the network use. So this is how things are done in France, for example.
Okay, thank you. I think we are at the end of the session. Thank you, everyone, for this webinar.